All right, so chemists, we are going to study the different reaction types in this lecture. So we went over this in class. This is just hammering home what we learned. All right, pen, what color do we want? Sort of in a purple mood today. So combination reaction. What is a combination reaction? So here, two or more reactants, and this is going to be kind of a longer lecture today, guys. Reactants combine to form a single product. These are easy to recognize because there is only one product at the end. All right, and so this can be written as A plus B makes A B. So combination is like a marriage. Two substances combine together to form one. So how do we predict the products of a combination reaction? Well, if I have Na solid plus Cl2 gas, now I might want to just say, okay, this is going to come together, and make NaCl2. However, that's not right. We need to look, Na is a metal, Cl is a nonmetal. We're going back to like the end of first term, beginning of second term here. So metal and nonmetal, what type of bonding is that? So, okay, metal, nonmetal coming together, that's ionic. We look at the periodic table. Na has one valence electron, and it will lose that one valence electron and have a +1 charge. Cl minus has 7 valence electrons. So we look in the after we look in the periodic table, it's going to want to gain one. So our first step is for ionic compounds, look at charges to figure out the product. All right, so this is not NaCl2. I have +1 and -1. Those balance out perfectly. So my product is NaCl. Now we go back to what we learned last lesson in balancing chemical equations. 1 Na on the reactant side, 1 Na on the product side. Na is good. Oh, but I have 2 Cl's on my reactant side. 1 Cl here. I need to put another NaCl over here. Okay, so now I have 2 Cl's on both sides, but I only have 1 Na on the reactant side, 2 on the product side. So I add another Na here. So you get 2 NaCl plus Cl2 makes 2 NaCl. So that is the step where we use coefficients to balance. All right. So I went through that kind of fast. You might want to pause, rewind, go back, and figure that out. So decomposition. A compound breaks down as a result of chemical change. These are easy to spot. There's only one reactant. The problem is the products are hard to predict. All right. So in combination, it was very easy. You could just use ionic charges, or in the case of molecules coming together, you can use Lewis dot structures and your Honk rule to figure out what the products are. Here, it's much harder to figure out what the products are going to be. So you don't have to. We will tell you. So here, an example of a decomposition would be the opposite of a combination. You have substance AB makes A plus B, and this is like a divorce or a breakup. So pretty straightforward. One substance breaking into many, the products of which are difficult to predict. Single exchange or single replacement. So here, a compound breaks apart, and one part combines with the other reactant. Okay, the reactants that change here tend to be metals. And we'll see some reactions in which that happens. Okay, so an example of here is we have A is by itself and BC together as a compound. So what happens in a single replacement is that A kicks the B out and A takes B's place. Think of this as like cheating, right? So B was cheated, or C cheated on B with A, and they came together, and B is now lonely and by itself. But in all honesty, probably better off by itself because C is kind of a cheating jerk. So that's a single replacement. Within the name, it just says single. One thing is replaced. So how can we predict single exchange products? All right, so I said before it's probably going to be the metal that's going to kick it out. So Mg is going to kick out AgNO3. Here, you can look on the back of your periodic table. Go way back. This is nitrate with a charge of -1. So I have metal with a nonmetal, so that means this is ionic. So what is my charge of Mg? Look on the periodic table. Mg has 2 valence electrons. Mg is going to be +2. The silver nitrate's a little trickier because AgNO3, Ag is not one that you can predict the charge of from its valence electrons. So we have to look at NO3. Well, NO3 is -1, and I have 1 Ag, and since the charges have to balance, I know that this is going to be +1. All right, so Mg is going to kick out silver. So let's just start by silver being by itself as a solid. It's a good way, if we have silver nitrate, we can get solid silver out of it. But now I'm left with +2 and -1. So my other compound is not just going to be MgNO3, it's going to be MgNO3 2. See how I did that? I used my charges. I balanced the charges to get MgNO3 2. Now, in a different color, let's balance. Blue is very different than orange. So I have 1 Mg here, 1 Mg here, that's fine. 1 Ag here, 1 Ag here, that's fine. 1 NO3 here, 2 NO3s here. Okay, so I'm going to need another AgNO3. So now my NO3s are checked. But now I have 2 Ags here, and I only have 1 here, so add another over here. And I'm balanced. So that stays as a 1, this becomes a 2, and this becomes a 2. All right. So this is a little more complicated because you have to recognize that it's a single replacement and then predict the products. It's requiring you to take some of the things you learned earlier in the year and bring them into our current understanding of chemistry. All right. So double exchange. Both reactants break apart. parts recombine into two new products. So you have two things. The reactants switch parts. So the way this can be written is AB plus CD makes AD plus CB. Now, the way I wrote it like this, if these are ionic compounds, and in double replacement, double exchange, they tend to be ionic. We have metal and nonmetal, metal and nonmetal. So the A and the C are just going to switch places. You can also think of it as the B or the D switching places. So here, metal, you're always going to have metal, nonmetal, metal, nonmetal. And I prefer to think of this as the partner swap. Back in the day, there was this terrible show called Wife Swap, which I always found super sexist. Why is it wife swap? Why aren't the husbands swapping? Why does it, like, it totally demeans the woman in that situation? I mean, that just demeans marriage. It was a terrible idea for a show. But let's not be heteronormative, and let's not be sexist. So we're going to call this one the partner swap. Okay, so predicting double exchange products. This, I believe there's what's called a solubility table on the back of your periodic table. So I have lead nitrate here and potassium iodide, and I have solutions. Double exchange is going to be solutions. What you're going to get is you're going to get two solutions, and on the product side you're going to have one solution and one solid. So you have to look at the solubility chart on the back of your periodic table. And we'll go over this in class. Okay. So, predicting the products. First, we're just going to make the ionic compounds. So, PB, well, NO3 from the previous slide we know is -1. K has 1 valence electron, so that's +1. I has 7, so it's going to gain 1 to have 8, -1. So I have two -1s, which means PB must be +2. All right. So, switching partners. All right. So, K is +1, NO3 is -1. So we get KNO3. PB is +2, I is -1, plus PBI2. And now we balance. So I have 1 PB on this side, 1 PB on this side. That's good. 2 NO3s here, only 1 here. So KNO3 gives me 2 NO3s. On this side, I have 2 Ks. This side I only have 1, so I need to add another Ki. So Ks are balanced, and now I's 2 here, 2 here. So we're good. So it's 1, 2, 2, 1. Now, when I look on the back of my periodic table chart, I'll notice that anything with potassium and nitrate is always soluble. So that means this is my solution. Lead with iodine in certain cases, this is always insoluble. So that's going to be my solid. Okay. So how does this relate to toxins? Well, toxins can react in any of these ways in the body, depending on the toxin and the circumstances. So if we look at, when we looked at kidney stones were a lot like this double exchange reaction, where you have a solid being formed, that awful, awful solid that gets formed in your kidneys. So here's just a summary of the reaction types. Combination here, we have two things coming together, carbon dioxide and sodium hydroxide. We have a gas and a solution becoming a solution. Decomposition, we have calcium carbonate, and if we heat it, we're left with calcium oxide solution and carbon dioxide. Single exchange, this is one of those rare cases where it's not the metal. So we have chlorine gas replacing bromine gas. Generally, it's going to be a metal that we see. And then Br is by itself. And here we have silver chloride. And this should not be exactly what I have. It should be like silver nitrate and barium bromide. So this is going to be AgBr, which is a solid, and barium nitrate. Sorry about that. Okay, so we have a solution of silver nitrate plus a solution of barium bromide comes together, and we get that solid that forms and a solution left. Again, here are the general ways of doing it. I think you have these all written down before. All right, wrap up. How do atoms rearrange to form new products? Well, chemical reactions can be sorted into categories. And these categories, you can write down, what I might do on your periodic table is write down this right here to get you the basic format. I don't want you to have to memorize it, but just understand how atoms can rearrange with one another to make new products. And the four general types of chemical reactions are combination, decomposition, single exchange, and double exchange. So I want to add one more thing in here, and it's called the Brinkelhoff twins, which is a silly name, or the 7+1 club. So when predicting products, certain elements are found as diatomic when by themselves. And you actually already know this. Like oxygen gas is not oxygen, it's O2. The key is when by themselves, not in a compound. But there are ones that if you are writing the prediction, or if you're predicting a product, or it says like oxygen gas reacts with, and these are the Brinkelhoff twins. So bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine. Or they say 7+1 club. So it makes a 7 on the periodic table. NOFCl, Brinkel, Br, and I. AT technically would too, but there's never really much of it present. And H is the +1, 7+1 club. So Brinkelhoff twins is because they're always diatomic. By themselves, a lot of you guys are going to see this and like, oh, it's always O2. But you know that like water is H2O. There's only one oxygen. But O2 by itself, the gas, is O2. All right. Sorry, that was just a little aside.